Alright, let's just jump right into a question that's kind of wild when you think about it. Every single year we connect billions, and I mean billions, of new devices to the internet. Your phone, your watch, your car, maybe even your fridge, and every single one needs its own unique address to get online. So how in the world has the internet's address book not just completely exploded? It feels like it should have run out of pages a long time ago. But the answer is this really cool story about a clever temporary trick and a very slow upgrade that's happening right under our noses. And this, right here, is the core mystery we're going to unravel. We have this fixed, limited number of addresses, but this absolutely endless demand for more. Seriously, we should have hit a brick wall years ago. So how are we all still getting online? Well, to really get the solution, first you got to understand just how big the problem really is. You see, the original system for handing out these addresses is called Internet Protocol version 4, or IPv4 for short, and it has a hard limit, a ceiling, only about 4.3 billion unique addresses. Now, back in the 80s, that probably sounded like an infinite number, but today that's actually less than the number of people on the planet, let alone devices. Now hold that 4.3 billion in your head and look at this. By 2030, we're expecting over 30 billion connected Internet of Things devices. And that's not even counting our phones or laptops or all the servers that make the internet run. The bottom line is, we have way more devices than original addresses. The math just doesn't add up. And listen, this wasn't some hypothetical problem for the future. This chart shows you the exact moment the crisis hit. Way back in 2011, the main global group that hands out big blocks of new IPv4 addresses, well, they officially ran out. The well went dry. So if the main supply has been gone for over a decade, how is your brand new smart speaker getting online today? The internet didn't just grind to a halt because some very smart engineers came up with this brilliant, even if it is a little messy, workaround. It's a technique that basically lets a whole bunch of devices hide behind a single address. And trust me, you use it every single day without even knowing it. It's called Network Address Translation, or NAT. The easiest way to think about it is like a receptionist at a big office. Inside the office, every single person has their own private phone extension, right? But to the outside world, there's just one main phone number for the whole company. NAT is basically the internet's version of that receptionist. And here's how it works right in your own home. Your Wi-Fi router, it gets one single public IP address from your internet provider. But then it acts like its own little post office, handing out private internal addresses to your phone, your laptop, your TV, you name it. When your phone wants to go to a website, your router swaps that private address for its public one, sends the request out, and when the data comes back, it remembers, oh yeah, this goes to the phone. All of your devices get to share one public identity. Okay, so that's how it works for a few devices in your house. It's pretty neat, but now take that idea and scale it way up. Imagine your internet service provider using that exact same trick, not just for your house, but for you and thousands of your neighbors, all at the same time. And yup, that is exactly what they do. It has a name, Carrier Grade NAT, or CGNAT. So instead of giving every single customer their own unique public IP address, they put a whole neighborhood behind a small pool of shared public ones. It is NAT on a massive scale, and it is one of the biggest reasons the old internet is still chugging along. But this trick has some serious drawbacks. The internet was originally designed on this beautiful idea that any two computers could talk directly to each other. NAT kind of breaks that. It makes things like hosting a game server from your PC or trying to access your home security camera a huge headache. And get this, if someone you're sharing an IP address with does something bad online and gets banned from a website, you might get banned too, just because you were in the same address pool. So CGNAT is a clever patch for sure, but it's not the real fix. The real long-term solution is a completely new version of the Internet Protocol, one that was designed from the ground up to have a virtually infinite number of addresses. Say hello to IPv6, and the numbers here are they're staggering. We're not talking about just doubling the addresses. We are going from 4.3 billion to 340 times quadrillion. That number is so big, it's more addresses than there are grains of sand on planet Earth. It's enough to give every single atom on the surface of the planet its own IP address, with tons to spare. The problem of running out? With IPv6, it is solved forever. Now, I know these new addresses look way more complicated, right? They're longer, they use letters and numbers, but they've got this neat little trick built in. If you have a long string of zeros in the address, like in this example, you can just squish it down and replace it with a double colon. It's just a handy little shortcut to make them a tiny bit easier to read. Which of course brings us to the most obvious question in the world. If IPv6 is so much better and it completely solves this massive problem, why are we still even talking about IPv4 and all these NAT tricks? Why haven't we all just switched over already? Well, because as this chart shows you pretty clearly, the transition is happening at a snail's pace. I mean, after more than a decade of trying to get this going, less than half of the world's internet is using IPv6. The majority of the network is still running on that old system, being held together by those clever NAT workarounds. And this quote really nails the problem. It's not that people don't get it. For years, the experts thought if they just kept explaining how we were running out of IPv4 addresses, everyone would magically switch. But, that's just not how people work. There's something called the education fallacy. Just knowing something is better isn't enough to make you change. Think about it. The people who run these huge networks are busy. They're always going to take the path of least resistance. And for a long, long time, the easiest path was just to stick with what they knew, IPv4, and just add another layer of that NAT trick. IPv6, even though it's better, looked like a complex, expensive headache with no immediate payoff. And the transition itself isn't like flipping a single switch. There are all these different ways to do it, and as you can kind of see from this table, each one comes with its own technical problems and trade-offs. So for a busy network operator, just adding more NAT can seem like the simplest choice, at least in the short term. So where does all of this leave us? It leaves us right here, with an internet that is, for the foreseeable future, this messy, hybrid creature that's kind of living in two different worlds at the exact same time. So to wrap it all up, the answer to how the internet still works is really a two-part answer. First, we have the clever but flawed trick of NAT, which is letting us stretch that old IPv4 system way beyond its breaking point. And second, we have this slow, gradual, and mostly invisible transition to the limitless world of IPv6 happening in the background. And that leaves us with one last big question to think about. The entire history of the internet is a story of constant innovation. But is our future going to be one where we finally finish the upgrade to a truly modern network? Or will we just get better and better at finding new, clever ways to patch up a system that was designed over 40 years ago? The answer to that is really going to define what the internet looks like for decades to come.